Alright guys, flipped video here. So, sorry about the shadow. It's kind of late and there's no sun, so everything's coming from above. Okay, so page 9, I'm actually reading the notes from my computer. So page 9 from the chapter 3 notes, the ones that say they're chapter 4. Use example 1, use analytic methods to find the local extrema, the intervals on which the function is increasing, and the intervals on which the function is decreasing. And the first function that's given is this polynomial. And I only have a black pen handy, so we're not going to get colorful today. Local extrema. So that means maxes and mins, and we've already talked about that. So hopefully as soon as you hear that, you think derivative. So derivative of 5 is 0, negative 6x, and 3x squared. And we learned a theorem that told us that in order for there to be a local max or min, this must be 0. So the derivative must be 0. So let's take out a 3x, and then I'm going to switch the order just because that's the way I like to write it. So if I take out a 3x from here, I'm going to have an x. And if I take out a 3x from here, I'm going to have a minus 2. And I can see that this thing is 0 when x is 0, and also when x is 2. So next I need to make a number line to see what's happening surrounding these. Remember, these are called critical numbers. And remember, critical numbers are places where the derivative is 0 and also where the derivative is undefined. Everybody forgets about the undefined part because it doesn't happen all the time. Most of the time we're looking at polynomials, and polynomials are defined everywhere. So I want to see what's happening on either side of 0 and on either side of 2 so I can determine if there is a maximum or a minimum or neither. So I'm going to make a number line, and similar to what we did when we were solving nonlinear inequalities, so like quadratic inequalities or rational inequalities, we're going to pick some test numbers, anything to the left of 0, anything between 0 and 2, and anything to the right of 2. You can pick whatever numbers you want. I like to pick the most simple ones. I'm going to plug them in, and again, similar to what I was just talking about, I don't care about the value, all I care about is the sign. So if I plug a negative 1 into the 3x, I get a negative, and if I plug a negative 1 into this factor, I also get a negative. These are being multiplied together. Negative times a negative is a positive. If I plug a 1 in here, I get a positive. If I plug a 1 in here, I get a negative, and a positive times a negative is a negative, and then here I would have a positive, positive, so positive. And I'm sure I've said this before, although I'm talking about the future at one time right now because it's Thanksgiving break when I'm making this video, but oftentimes it alternates positive, negative, positive, or negative, positive, negative, but not always, and I will be sure to find one for your quiz and or test that does not. So don't just say, oh, there's a positive there, I don't need to do anything with these two because I know it's going to alternate, because it very well may not. So this positive is referring to the derivative. We're saying the derivative is positive. So what does it mean when the derivative is positive? Right, it means that the function is increasing. So positive slopes, tangent lines are all positive here. Function is going up. Slopes are the derivative, and what the behavior is actually the function. And then it switches to it being the derivative, and I'm sure I'll say this 1,000 times also, do not use the word it. Tell me what you're talking about. It could be either the derivative or the function, and in the next section it could even be the second derivative, so we don't want to say it. So the derivative changes to negative. Negative slopes means function is decreasing. So at 0, at x equals 0, there is a relative maximum. So at x equals 0, can you still see that? Yes. There is a relative maximum. Okay. So let me go back here for a second again. The derivative is negative, meaning slopes of tangent lines are negative. The function is decreasing. Common mistake people say is derivative is negative means derivative is decreasing, and that is incorrect. Derivative is negative, slopes are negative, means the function is decreasing, the function itself. And then at 2, it changes, the derivative changes to positive. So we have a switch to going up. Derivative is positive, means the function is increasing. And if I change, so here would be x equals 2. And of course, I have no idea if this is what the graph looks like. This is just a sketch to give you an idea of what's going on. If the derivative changes from negative to positive, the function decreases, then increases. That means there is a local or relative, same difference, min. Local and relative mean the same thing. So at x equals 2. So let me go back and read the question. It asks for local extrema. It doesn't say where do the local extrema happen. It asks for local extrema. So far, all I've said is where it happens. So I'm going to cover my bases because it's not 100% clear. I'm going to cover my bases and I'm going to say what the actual maximum value is. So I want to know what this value is. Do I want to plug this into the... Do I want to plug this x equals 0 into the derivative or the function if I want to know what this value on this point is right here? I'm going to plug that into the function itself. I want to know the y value. Think of a graph, right? Let's pretend this is a graph. And again, I have no idea if this is what this graph looks like exactly. It's just a sketch, but I want to know what this maximum value is. I want to know this y value here. That would be the y max. Same thing for the when x equals 2. I want to know what this minimum value is. And again, it's a relative min. We know an x cubed graph looks like this. It's going to go down forever and up forever. So it's not an absolute because this goes down forever. There is no absolute min. And this is not an absolute max because this goes up forever. There is no absolute max. So I want to know what this minimum value in this little neighborhood, right, local neighborhood, I want to know what it is, so I want to know the y value. The y value is the function, not the derivative. So I'm going to plug in a 0. I'm going to say is. I can plug in a 0 without writing anything, right? So the relative max is 5 at x equals 0. And then let's see if I can use my brain, unlike the last video I made. What is this going to be? 2 squared 4 minus 12, so 5 minus 12 is negative 7, plus 8, so 1. So 1. So this would be a fairly good, well, aside from the fact that this isn't x equals 0, so the y-axis would be right there, right? But that could be a decent sketch of, this would be a 5 and this would be a 1. So that's just part A. And you're like, oh my gosh, that's all just for part A. Well, really, we already have the answers to B and C. So let me scoot up a little. Based on the number line, I can tell where the intervals on which the function is increasing. Now, I have this graph here, right, that I've drawn a sketch of. That can help me, but that can't be my answer. Remember, I've told you numerous times before that you can never use a graph as justification for anything. You need to write it in calculus. Same thing with the number line. You need to state what this number line means. You need to interpret this and show that you know what this number line means. So part B asks for increasing. So I would say f, the function, is increasing on the intervals. So increasing is where the derivative is positive, negative infinity to 0. And 2 to infinity. And I need to give a reason because f prime is positive. F prime is positive means f is increasing. Okay? I don't want to do a bracket here because we showed that the derivative was equal to 0 at x equals 0 and x equals 2. 0 is not positive, right? For increasing, we're looking for positive slopes or positive derivative values. So I can't include the 0 and the 2. Some books will include the 0 and the 2. It kind of drives me nuts. And then f is decreasing, so whatever's left, right in here, between 0 and 2. Since, or because, if I want to stay consistent, f prime is less than 0. You always need to give this reason. Don't just tell me it's increasing somewhere. You need to tell me how you know it's increasing somewhere. Okay, so, oh, that took a long time. Okay, let's see if we can do this one. Oi, okay, let's see if we can do this one quickly. Second example. So we know these are sines and cosines are cyclic, and we'd have an infinite number of maxes and mins if we didn't limit our interval. So that's what's going on here. They're just saying only focus on in here, otherwise you're going to keep going forever and ever and ever. So maxes and mins, I know I need to take a derivative. Set it equal to 0. If I solve that, I would subtract 1 and divide by -2. So I want to know where cosine is equal to 1/2, anywhere between 0 and 3 pi. So that's a full revolution plus another half, right? 2 pi plus another pi. So what's the reference angle for cosine 1/2 would be what, 60? So I'll write them in degrees and then we can switch them to radians. So when cosine is 1/2, we have a 60-degree angle. So it's positive in the first quadrant, 60. And cosine is also positive in the fourth quadrant, right? Because cosine is the x value. So if I have a 60-degree reference angle on the fourth quadrant, I'm at 300 degrees. And then again, if I'm going another half circle, I would be 360 plus 60, 420. So let me show you what's going on. I've got a 1/2 in either of those. This is 60. That's the first angle. This is 360 minus 60, right? That's the second angle. And then this is 360 plus 60. 3 pi is right here. So the x value is negative, so I can't go any further. So what is this? I know this is pi over 3. I know this is 5 times that, so this is 5 pi over 3. And I know this is 7 times that, so this is 7 pi over 3. So that's where I have zeros of the derivative. So now I'm going to go and do my number line. And pick some test numbers. So I think better in degrees. I'm going to say degrees. So I know this was 60, so what's between 60 and 300? That's easy. How about 180? And what's between 300 and 300 and 420? That's easy. How about 360? And then beyond 420, let's say 450. That would be like a 90-degree reference angle. And then I want to know what the derivative is at those values. So I've got to go and plug these four. Oops, I didn't do 360, did I? 360. Okay, so cosine of 30 is rad 3 over 2. Write this out. I don't want to take forever on this video. It's already longer than I wanted it to be. So if you're not sure, write this out. So I'll write one of them out. F prime of 30, so plugging in here, would be 1 minus 2 cosine of 30. And if you're better in radians, do it in radians. Cosine of 30 is rad 3 over 2. That cancels out. Rad 3 is clearly bigger than 1 because it's bigger than rad 1. So 1 minus larger would be negative. So 180, what's cosine of 180? Negative 1. So this is going to be 1 plus 2, that's positive. 360, that's positive 1. Cosine of 360 is positive 1, so this is 1 minus 2, that's negative. And 450 is like 90, because I can trash a 360, right? Cosine of 90 is what? 0? Yep, had to think about that one for a second. So this is 0, so that's positive. So alternating. So I can summarize the answers. I'll do it over here. Switching from, so remember it asked for relative extrema, so maxes and mins. Switching from negative to positive, so slopes are negative to positive, there's going to be a min, so local or relative min is I'll leave a blank at what